Today's topic is alkenes from modern organic chemistry by Dr. J.M. Sehgal. Introduction. There are a number of homologous series of open chain hydrocarbons in which the different members contain lesser number of hydrogen atoms than the alkanes having the same number of carbon atoms. Since they contain less than the maximum possible number of hydrogen atoms, such hydrocarbons are termed as unsaturated hydrocarbons. The unsaturated hydrocarbons having the general formula C and H2N are called alkanes. They are characterized by the presence of a double bond between two carbon atoms in the molecule. It is known as ethylenic or olefinic bond. Unlike alkanes, alkenes are quite reactive chemically. They can rapidly undergo reactions in which a molecule of the attacking reagent is added to the alkane molecule to form a product containing more atoms than were present in either of the reactants. For instance, ethylene, the first member of alkene series, react with the chlorine to form a product with the formula C2H4Cl2. Since this product is an oily liquid, ethylene was also termed as olefiant gas, that is oil forming gas. Thus, this series beginning with ethylene began to be referred to as olefin by the earlier chemists. It is interesting to recall that cycloalkanes also have the general formula CnH2n. Thus, alkanes, which are open chain unsaturated hydrocarbons, are isomeric with cycloalkanes, which are cyclic saturated hydrocarbons. Structure of alkenes. Alkenes are marked by the presence of a carbon carbon double bond in their molecules. The doubly bonded carbon atoms are in a state of sp2 hybridization, as illustrated below by considering the structure of ethylene, the simplest alkene. The two carbon atoms of ethylene which are linked by double bond make use of three equivalent sp2 hybridized orbitals and an unhybridized p orbital in the formation of this molecule. One of the carbon-carbon bonds of ethylene is formed by the overlap of an sp2 orbital of one carbon with an sp2 orbital of the second carbon. Each of the four carbon hydrogen bond is formed by the overlap of one of the remaining hybridized orbital of each carbon with the 1s orbital of a hydrogen. The bonds thus formed are sigma bonds as the overlapping of orbital take place along their axis. Moreover, since all the three sp2 hybrid orbitals of each carbon lie in the same plane, all the carbon and hydrogen atoms of ethylene are also coplanar. Thus, ethylene is a flat molecule in which each carbon is situated at the center of a triangle, at the corners of which are located two hydrogen atoms and the other carbon atom, as is clear from the skeleton of the molecule. Now, each carbon atom is left with an unhybridized half-filled p orbital at right angle to the plane in which the carbon and hydrogen atoms are lying. These p orbitals of the two carbons overlap sideways to form another carbon-carbon bond. Since the overlapping takes place only to a small extent in its formation, this bond is a weak pi bond. The bond consists of two electron clouds, one lying above the plane of carbon and hydrogen atoms and other below it. It is evident that the two bonds comprising the double bond between carbon atoms are not equally strong. The sigma bond between the carbon atoms has a strength of about 398 kJ mole inverse, while the pi bond has a strength of nearly 284 kJ mole inverse. The total strength of the carbon-carbon double bond of ethylene, 682 kJ mole inverse, is no doubt greater than that of carbon-carbon bond single bond ethane, 368 kJ mole inverse. Each of the hydrogen carbon hydrogen bond angles is ethylene is 117.5 degree, while each of the carbon carbon hydrogen bond angles is slightly more than 121 degree. The carbon-carbon double bond distance of ethylene is 134 picometer, which is lesser than the carbon-carbon single bond distance. This is because the effective size of sp2 orbital of carbon which is involved in the formation of carbon-carbon double bond is lesser than that of sp3 orbital which take part in the formation of carbon-carbon single bond. As a result, length of the bond formed by the mutual overlapping of sp2 orbitals is shorter than the length of the bond formed by the overlapping of sp3 orbitals. Moreover, the sideways overlapping of p orbitals to form the pi bond also brings the carbon atoms closer together. again due to the smaller of sp2 orbitals in comparison with the sp3 orbitals. The carbon hydrogen bond distance in ethylene 109 picometer is less than in ethane 110 picometer. Nomenclature. The common system. In this system, alkenes are given the general name olefins. The individual members are named by replacing the suffix "-ine" of the corresponding alkene by "-ylene". In case of isomeric compounds, the position of the double bond is generally integrated by using Greek letters alpha, beta, gamma, etc. according as the double bond is at one end of the chain or increasingly away from it. Sometimes prefixes such as iso are also used for balanced chain isomers. The common name of some alkenes are given ahead: CH2, methane, and common name methylene, ethane, ethylene, propane, propylene, butane, alpha butylene, butane, beta butylene, butane, isobutylene, pentane, alpha pentylene, pentane, beta pentylene, hexane, alpha hexylene. IUPAC system. According to this system, the class name of the common compound is alkenes and the individual members are named as follows. The longest chain containing the double bond is chosen as the parent alkene and the corresponding word root is noted. The suffix "-in" is added to the word root to denote the presence of carbon-carbon double bond. The carbon chain is so numbered that the carbon atom preceding the double bond gets the lowest possible number, and this number indicates the position of the double bond. The number indicating the position of the double bond is placed just before the name of the parent alkene or just before the prefix "-ine". For example, 1-butene or but-1-ine. In case of complex molecules, the number representing the double bond is always just before the prefix are exemplified above. The names and position of the side chains, if any, suitably indicated before the name of parent alkene in alphabetically order. For example, 4-methyl 1-pentene, 2-ethyl 1-pentene, 4-ethyl 5-methyl 1-hexane. If the same chain is repeated two or more times, the prefix di, tri, etc. is added to the name of the side chain, but the prefixes di, tri, etc. are not taken into consideration while deciding the alphabetically order. For example, 5-ethyl 2 for dimethyl 3-heptane. The IUPAC names of the first few alkenes are given ahead: methane, ethene, propene, 1-butene, 2-butene, 2-methyl 1-propene, 1-pentene, 2-pentene, 1-hexene. Alkenyl groups. The monovalent groups obtained by removing a hydrogen atoms from a doubly bound carbon atom is known as alkenyl group. To obtain the name of a particular group, the terminal E of the name of parent alkene is replaced by "-yl". For example, ethanyl, propenyl, 2-propenyl. In case of monovalent groups obtained by removing a hydrogen atom from a carbon other than the doubly bound carbon, the groups are usually known as by specially names, for examples allyl or 3-propenyl. Isomerism in alkenes. Structural isomerism. The first two members of alkenes, ethylene and propylene, do not show structural isomers, but the alkyne from C4H8 onwards can exhibit chain isomerism as well as position isomerism. There are three structural isomerism possible for the molecular formula C4H8: 1-butene, 2-butene, 2-methylpropene. It is clear that 1 and 2 are position isomers of each other, 1 and 3 are chain isomers, while second and third show position as well as chain isomerism. Similarly, C5H10 can have 5 structural isomers: 2-methyl 1-butene, 1-pentene, 3-methyl 1-butene, 2-pentene, 2-methyl 2-butene. Alkenes also show ring chain isomerism with cycloalkanes, for example, propene, cyclopropene. Hindered rotations around carbon-carbon double bond, geometrical isomerism. The carbon-carbon double bond in ethylene and other compounds consists of a sigma bond and a pi bond. The pi bond involves the overlapping of unhybridized pi orbitals of the two carbon atoms above and below the plane of the atoms. Because of this type of overlapping, rotations around carbon carbon double bond is strongly hindered and can take place only if the pi bond breaks. But this would require about 284 kilojoule of energy per mole, which is not available to the molecules at room temperature. Due to hindered rotations around carbon carbon double bond, the relative positions of group attached to doubly bonded carbon atoms get fixed. As a result, several higher alkenes and other substituted products can exhibit geometrical isomerism, that is, they can exist in two distinct isomerism form which differs from each other in the relative distributions of groups in space around the double bond. For example, 2-butene can exist in the following two forms: cis 2-butene, trans 2-butene. Relative stabilities of alkenes. Even though all alkenes contain a carbon carbon double bond in their molecule, different alkenes have appreciably different stabilities. Their relative stabilities are generally determined on the basis of heats of hydrogenation. Heat of hydrogenation of an unsaturated compound is the quantity of heat evolved when 1 mole of the compound is completely hydrogenated. It is the value of nearly 125 kilojoule for almost every alkene, though the actual value varies slightly from one member to another as shown in table. These values give quantitative information about the relative stabilities of alkenes. For instance, the heat of hydrogenation of trans 2-butene is 115 kilojoule, while that of cis 2-butene is 119.6 kilojoule. Each of these reactions uses up 1 mole of hydrogen and gives the same product, that is N-butane. Still, if trans 2-butene evolves about 4 kilojoule of energy less than cis isomers, this means that it contains about 4 kilojoule of energy less. Therefore, it must be more stable of the two isomers. Similarly, any other alkenes which has lesser heat of hydrogenation than another isomer must be more stable. Thus, the heat of hydrogenation of different alkenes led to the following conclusions. In case of dialkyl derivatives of ethylene which exist as geometrical isomers, a trans alkane is slightly more stable than the cis isomers. This is because in the trans isomers the two larger substituent groups are far apart from each other as compared to cis isomer. Therefore, there is lesser crowding and lesser van der Waals strain in trans isomers and has greater stability. For example, trans 2-butene, cis 2-butene. The more the number of alkyl group attached to the doubly bound carbon atoms, the greater the stability. Therefore, the order of reactive stabilities is as follows. The above order can be explained in terms of hyperconjugations. The greater the number of alkyl group attached to a doubly bound carbon atoms, more is the number of alpha hydrogens, therefore greater is possibility of hyperconjugative interactions. This in turn would give rise to greater number of resonance structures, or in another word, more extensive delocalizations. Hence, such alkenes would acquire greater stability. For example, 2-butene, 2 alkyl groups attached to doubly bound carbon atoms, 6 alpha hydrogen, more hyperconjugative interactions, greater stability. 1-butene, 1 alkyl group attached to doubly bound carbon, only 2 alpha hydrogens, lesser hyperconjugative interaction, lesser stability. General method of preparation. The alkenes, particularly the lower members, are obtained commercially by the cracking of a higher fractions of petroleum followed by fractional distillation. In addition, different laboratory methods are also available for their preparation in a pure form. Most of these methods involves elimination of appropriate groups from adjacent carbon atoms as discussed below. Dehydrohalogenation of alkyl halides. This reaction involves the removal of element of hydrogen and halogen from adjacent carbon atoms of an alkyl halide by treating it with an alcoholic solution of potassium hydroxide. For example, ethyl chloride with the alcoholic potassium hydroxide give ethylene plus potassium chloride plus water. Mechanism. The dehydrohalogenation of alkyl halide take place as follows. The base such as hydroxide ions obtained from alcoholic potash abstract a proton from a beta carbon. that is the carbon which is next to the carbon carrying the halogen atom. At the same time, the halogen is eliminated as a negative halide ion, and the electron pair of the carbon hydrogen bond left behind after the removal of H positive ion is used to form the second bond between carbon atom as depicted below. It has also been observed that dehydrohalogenation generally involves the removal of a hydrogen and halogen situated in transposition with respect to each other as shown above. The energy required for the cleavage of carbon hydrogen and carbon chlorine carbon halogen bonds comes from, that is formations of bond between the base ions and the abstracted H positive ion, formation of second bond between carbon atoms, and the third is solvation of halide ions, which is accompanied by release of considerable energy. It should be noted that the reaction does not take place in the stepwise manner but involves a concentrated mechanism. This mechanism, commonly known as E2 mechanism, E for elimination, 2 for biomolecular, involves a single step biomolecular elimination process. The reaction follows second order kinetics, and the rate of reaction depends upon the concentration of both hydroxyl ions and alkyl halides. Orientation of dehydrohalogenation and ease of formation of alkenes regiochemistry. With several higher alkyl halides, the elimination of hydrogen from different carbon atoms is possible. This led to the formation of a mixture of isomeric alkenes in such cases. For example, secondary butyl chloride plus alcoholic potassium hydroxide gives 2 butene and 1 butene, where 2 butene is more stable and 1 butene is less stable. The mixture formed in such cases contains the most stable alkyl in predominating quantities. As already explained, the order of stability of alkenes is determined by the number of alkyl groups attached to the doubly bound carbon atoms. The more the number of alkyl groups, the greater the stability. As such, the relative order of stability is R2 carbon double bond Cr2 greater than R2C double bond CHR greater than R2C double bond CH2 greater than RCH double bond CH2 greater than ethene. This also represents the order of ease of formation of alkenes in dehydrohalogenation, since the more stable the alkene, the more easily it is formed. The above observation can be justified in terms of the transition state leading to the formation of the alkene. It may be seen that in the transition state, the double bond between carbon atom has begun to form, and therefore the transition state has acquired some of the alkene character. As such, the alkene in the transition state would have the same order of stability. Now, a more stable transition state would have lower E activation and would be therefore formed more easily. As such, the more stable alkene would also be formed more easily. Sadzev rule. Sadzev gave a generalization to predict the orientation of dehydrohalogenation on the basis of relative stability and ease of formation of possible alkenes. According to Sadzev rule, when an alkyl halide can undergo elimination in two different ways, forming a mixture of two products, the preferred product is the alkene, which is more highly alkylated at the doubly bonded carbon atom. For instance, in the dehydrohalogenation of secondary butyl chloride, 2-butene is the preferred product as it is more alkylated and therefore more stable and easier to form than 1-butene, which is the other product formed. Reactivities of alkyl halides in dehydrohalogenation. It has been found that for alkyl halides with a given alkyl group, the rate of eliminations varies with the nature of X in the order Ri greater than Rbr greater than Rcl greater than Rf. For a given halogen atoms, the order of reactivity of different alkyl halide is tertiary, then secondary, and then primary. This is because branching of the carbon carrying the halogen increases in going from primary to secondary to tertiary alkyl halide. Now, the greater the branching or greater the number of beta hydrogens which can be attacked by the base, and therefore the higher the probability of attack. Moreover, the more branched alkyl halides lead to more branched and therefore more stable alkene. Now, the transition state for more stable alkene is also more stable and requires lesser reactivations. This means that ease of elimination is maximum for tertiary alkyl halides. Next comes secondary, while the primary halides come last. E2 mechanism. Some secondary and tertiary alkyl halide undergo halogenation in a solution of low base concentration by a different mechanism known as E1 mechanism, E for elimination, 1 for unimolecular. This mechanism operates through a two-step process in which the rate determining steps involves only one molecule. It is believed that the first step, which is a slow rate determining step, the alkyl halide dissociates into halide ions and carbocation. In the second step, which is the fast one, the carbocation loses a proton to H negative ion to form the alkene. It is obvious that the reaction follows first order kinetic as the rate determining step involves only one molecule. The rate of the reaction is independent of the concentration of the base and varies only with the concentration of alkyl halide. Dehydration of alcohols on heating with sulfuric acid or phosphoric acid on passing their vapor over heating alumina or Lewis acid, alcohols get dehydrated to form alkene. The exact reaction conditions vary with the nature of alcohol taken. Ethyl alcohol with 96% of H2SO4 at 443 Kelvin temperature give ethylene. Tertiary butyl alcohol with 20% of H2SO4 at 355 Kelvin give 2-methylpropene plus H2O. Mechanism: the dehydration of alcohol is a unimolecular elimination reaction which involves the formation of a carbocation as an intermediate. The reaction is believed to take place in three steps. In the first step, alcohol combined with the hydrogen ion to form a protonated alcohol. The second step involves the dissociation of a protonated alcohol and the formation of carbocation. Finally, the carbocation loses a hydrogen ion yield alkene. The various steps are illustrated below. Ethyl alcohol plus acid gives protonated alcohol. Now, protonated alcohol gives carbocation plus water. Now, protonated carbocation gives ethylene. All these three steps above involves reversible equilibria. However, the resulting alkene is much more volatile than the starting alcohol and is easily driven out from the reaction mixture. This shifts the equilibrium in step 3 towards the right. Consequently, the entire reaction is pushed to completion. It may be noted that the dissociation of protonated alcohol requires a supply of energy. This is made available through the solvation of carbocation, considerable energy being released by setting up ions dipole bonds between the carbocation and solvent molecules. Evidence in support of the mechanism. The above mechanism is supported by the following observation: relative ease of dehydration of alcohol. It has been observed that the ease of dehydration of different classes of alcohol follows the order tertiary, then secondary, and then primary. This observed order can be justified in terms of the rate determining step in the process of dehydration, which involves the dissociation of protonated alcohol to form carbocation. It is apparent that the greater the stability and ease of formation of carbocation formed in the rate determining step, the greater the tendency of the alcohol to change into carbocation. Now, the order of stability and ease of formation of carbocation is tertiary, then secondary, and then primary. Tertiary alcohols undergo dehydration most readily because they form the tertiary carbocation, which is the most stable. Once formed, the carbocation readily changes into alkenes. In the same way, secondary alcohol would be more easily dehydrated than the primary alcohol, which would be relatively most difficult to dehydrate. Orientation of dehydration: regioselectivity. Many alcohols give rise to mixture of isomeric alkenes on dehydrations, but one of the alkenes is formed in predominantly largely amounts. Such a reaction which can yield two or more structural isomers, but it actually produces only one isomer as the sole product or the predominant product, is said to be regioselective. For example, dehydration of secondary butyl alcohol over H3PO4 on alumina at 298 Kelvin yields a mixture of 75.9% of 2-butene and 24.1% of 1-butene. Both the Isomeric butenes are obtained by the expulsion of a H positive ion from the same carbocation formed as an intermediate as shown below. Therefore, the stability of carbocations cannot have any effect on the highest than expected amount of 2-butene formed. It may be noted, however, that the 2-butene is more stable than 1-butene since the former is more highly substituted. This means that the reduced selectivity in the dehydration of alcohols is due to the greater stability of the main product. A similar situation exists in the dehydration of 2-methyl-2-butanol while with 15% of H2SO4 at reflux temperature. Here again, the more highly substituted product and therefore more stable product is formed in predominating quantities. To sum up, it may be stated that reduced selectivity in dehydration of an alcohol is consistent with the formation of more stable alkene, rearrange of carbocation, and formation of unexpected products during dehydration. It has been found that during the dehydration of alcohols, some of the alkenes formed are not one would what one would normally accept. The positions of the double bond forms or sometime even the carbon skeleton may be quite unexpected. For example, the dehydration of N-butyl alcohol gives a mixture of 2-butene and 1-butene, whereas normally 1-butene should be formed. The formation of unexpected product as shown above can be explained in terms of the rearrangement of intermediate carbocations. It has been observed that carbocations tend to rearrange to form more stable ions. This rearrangement usually involves the migration of a hydride ions from an adjacent carbon atom to the positively charged carbon of the carbocation. Such a migration is known as hydride shift. Alternatively, the rearrangement may occur through the migration of an alkyl group with its pair of bonding electrons from an adjacent carbon to the carbon having the positive charge. This type of migration is known as alkyl shift. Since such migration generally involves only adjacent carbons, they are also termed as one-two shift. Example of hydride shift: in the dehydration of N-butyl alcohol, the intermediate carbocation initially formed is N-butyl carbocation, which is a primary ion. This undergoes 1,2 hydride shift to form the more stable secondary butyl ions. This ions in turn loses the H positive ion to form the more stable 2-butene as the preferred product. Example of alkyl shift: in the dehydration of 3,3-dimethyl-2-butanol, the carbocation initially formed is a secondary carbocation, that is 3,3-dimethyl-2-butyl ion. This undergoes the migration of a methyl group with a bonding pair of electrons from an adjacent to the positive carbon to form the more stable tertiary carbocations, namely 2,3-dimethyl-2-butyl ions. The ion thus formed loses a hydrogen ion to form 2,3-dimethyl-2-butene as the main product, which is more stable than the expected product 3,3-dimethyl-1-butene. It may be pointed out that the dehydrogenation of alkyl halides, which proceeds by E2 mechanism, does not give rise to any unexpected product. As in case of dehydration of alcohol, as such, dehydrohalogenation is often preferred as dehydration method for the preparation of alkenes. Dehalogenation of vicinal dihalides: when heated with zinc in alcoholic solution, a vicinal dihalide, that is a dihalide containing two halogens on adjacent carbon atom, get dehalogenated to form an alkene. For example, ethylene bromide with the zinc on heating gives ethylene plus zinc dibromide. The major limitation of this reaction is that vicinal dihalides are themselves usually obtained by the addition of halogens to alkenes. As such, this is not a very practical method for the preparation of alkenes. Mechanism: dehalogenation is a bimolecular elimination reaction which proceeds as follows. Vicinal dihalides undergoes transition states and then form ethene plus zinc dichloride or dibromide. Controlled reductions of alkynes: the controlled reductions of an alkynes to the alkyne stage may be brought about with the hydrogen in the presence of a special catalyst, palladium supported or CCO3 partially poisoned by a lead acetate and known as Lindlar's catalyst, or a nickel boride catalyst known as P2, or with sodium or lithium in liquid ammonia, whereas the alkene can exist in cis or trans. From the catalytic reductions yields mainly cis alkenes, while the other method produces predominantly trialkene. For example, 3-hexane on with the H2 platinum CaCO3 or PU2 gives 6 3-hexene, and with liquid ammonia gives trans 3-hexene. The mechanism of trans addition with alkali metal ammonia is discussed in chapter 7. Pyrolysis of quaternary ammonium hydrides or Hofmann elimination. When tetraalkyl ammonium hydroxide is heated strongly 400 Kelvin or higher, it undergoes elimination reactions known as Hofmann elimination to form an alkene. The quaternary ammonium hydroxide used in the reaction are obtained by reacting an amine with excess of methyl iodide. The procedure is known as exhaustive methylation, followed by the reaction with silver oxide. For example, trimethyl and propyl ammonium hydroxide used in the above reaction is obtained as followed: and propyl amine with excess. Mechanism. The mechanism of Hofmann elimination involves the removal of a proton from a beta carbon with respect to nitrogen of the quaternary ammonium ion. At the same time, there is a rearrangement of electrons. Carbon nitrogen bond breaks and the carbon carbon double bond is formed. The mechanism is quite similar to that of dehydrohalogenation of alkyl halides. However, in contrast to dehydrohalogenation of alkyl halides, where more highly substituted alkenes is the major product, the alkene preferably formed in Hofmann elimination is the one that is the least substituted. 1-methyl butyl trimethyl ammonium hydroxide on heating is 1 pentene and 2 pentenes. The reason for this selectivity is not clearly understood, but it appears that OH negative abstract a proton from the least hindered position in the alkyl groups. Physical properties. Physical state. The first 3 members of alkenes are gases, the next 14 are liquid, while the higher members are solid, with the exceptions of ethylene, which have faint sweet odors. All other members are colorless and odorless. Physical constants. The boiling points of alkenes increase regularly with the increasing number of carbon atoms amongst isomeric alkenes. Branch chain members have lower boiling points. The melting points and specific gravities of alkenes also shows a regular gradation, but as in case of alkenes, the maximum specific gravity of alkenes is about 0.8. This means that all alkenes are lighter than water. Solubility. The alkenes are practically insoluble in water but freely soluble in organic solvents such as benzene, ethers, and carbon tetrachloride. Polarity. The trans isomers of symmetrical alkenes are non-polar in character, but the unsymmetrical alkenes and the cis isomer of symmetrical alkenes are somewhat polar and have small dipole moments. Being somewhat polar, cis alkenes have slightly higher boiling points than the trias isomers. On the other hand, being unsymmetrical, cis isomers are not too closely packed in the solid state, and therefore they have lower melting point than the trans isomers. Chemical properties of alkenes. The carbon-carbon double bond, which is characteristic feature of every alkene, consists of a strong bond, sigma bond, and a weak bond. As can be reasonably expected, the pi bond breaks up rather easily when attacked by chemical reagents, and two strong sigma bonds are formed in its place, as shown below. Thus, the typical reactions of alkenes are addition reactions, which involves the union of two reacting molecules to yield a single molecule of the product. A majority of the addition reactions of alkenes are initiated by electrophilic reagents, since the electron pair of the pi bond in alkenes serve as a source of electrons. But apart from electrophilic addition reactions, alkenes also undergo some free radical addition reactions and even some substitutions and cleavage reactions. The important reactions are discussed below. Addition reactions. Addition of hydrogens. In the presence of certain finely divided metals such as platinum, palladium, or nickel, hydrogen adds on to alkenes to form alkanes. The temperature and pressure employed in the reaction vary with the nature of a catalyst. The reaction proceeds quite rapidly in the presence of a suitable catalyst, but is very slow in its absence. The finely divided metallic catalyst helps the reaction by absorbing the reactant molecules on its anomalous surface and breaking the pi bond of the alkene. As already discussed, hydrogenation of alkenes is very useful in determining the relative stabilities of alkenes. Mechanism of hydrogenation. Hydrogenation of alkenes is a heterogeneous reaction which takes place on the surface of solid catalyst particles in a stepwise manner. To start with the catalyst absorbs hydrogen on its surface. This is followed the formation of a complex between the catalyst and the alkene by the overlap of filled pi orbitals of alkene with the empty orbital of the metal. A stepwise transfer of hydrogen atoms to the alkene then take place. The alkene thus produced finally diffuses out of the catalyst surface. It is interesting to note that both the hydrogen atoms add to alkenes from the same side of the molecules. This is known as syn addition. Electrophilic addition reactions. The important addition reactions of alkene which involves electrophilic addition mechanism are as follows. Addition of hydrogen halides. Alkenes readily undergo addition reactions with hydrogen halides to form alkyl halides. Ethylene with hydrogen iodide give ethyl iodide. Mechanism. The addition of hydrogen halides to alkenes take place by a two-step electrophilic mechanism. Step 1, which controls the overall rate of the reaction, involves the transfer protons, that is hydrogen without its electron, to the alkene to form a carbocation. In doing so, one of the doubly bond carbon atoms uses the pi electrons formerly shared with the other carbon, which is rendered electron deficient. This is followed by the step 2, in which the carbocation and the negative halide ions combines to form the final product. Addition to unsymmetrical alkenes. Markovnikov rule. In case of unsymmetrical alkenes, the addition of hydrogen halides and other similar reagent which consists of two different atoms or groups can give rise to two isomeric products. For example, when hydrogen iodide adds to propylene, formation of two products is possible as shown below: N-propyl iodide and isopropyl iodide. It is observed, however, that actually isopropyl iodide is the main product and N-propyl iodide is formed as in very small quantities. A careful study of many addition reactions of this type enabled Markovnikov to enunciate a rule known as Markovnikov rules. This rule states that when addition across an unsymmetric ethylenic bond take place, the positive part of the attacking reagent goes to the carbon with the greater number of hydrogen atoms. Theoretical justifications of the rule. Markovnikov rule can be easily justified in terms of the ionic mechanism of the addition reaction. For instance, let us consider the addition of hydrogen iodide to propylene, which yields isopropyl iodide to propylene, which propyl iodide which iodide as the predominant product. As stated above, the reaction can be initiated by the addition of electrophilic particle to one of the doubly bonded carbon atom to form either carbocation 1 and 2. Carbocation 1 is a secondary carbocation while carbocation 2 is a primary carbocation. On the basis of ease of formation and relative stabilities of carbocations, carbocation 1 would naturally be formed faster than the and in preference to carbocation 2. Reaction of this preferred carbocation with the iodide ion would yield isopropyl iodide as the main product. Similarly, in the addition of HCl to isobutylene, the product obtained is almost only tertiary butyl chloride. This is because the intermediate carbocation in the formation of tertiary butyl chloride is a tertiary ion 3, which is naturally formed in preference to other possible carbocation form a primary ion. As such, the final product is obtained by reaction between chloride and the tertiary carbocation. Modern version of Markovnikov rule. On the basis of our present knowledge of mechanism of addition reaction of alkenes, Markovnikov rule may also be stated that addition of ethylenic double bonds involves the intermediate formation of more stable carbocation. Anti-Markovnikov addition peroxide effect. It has been observed that in presence of peroxides, the addition of hydrogen bromide to alkenes take place against the Markovnikov rule. For example, when propylene is treated with hydrogen bromide in the presence of traces of benzoyl peroxides, the predominant product obtained is N-propyl bromide and not isopropyl bromide, expected according to Markovnikov rules. But if the addition of hydrogen bromide is carried out in the absence of peroxides, the reactions take place in accordance with the Markovnikov rules. The action of peroxide to cause the anti-Markovnikov addition of hydrogen bromide is known as peroxide effect. It was discovered by Kharaj. It should be carefully noted that peroxides have no effect in case of the addition of other reagents such as hydrogen chloride, hydrogen iodide, sulfuric acid, water, etc. free radical mechanism of anti-Markovnikov additions. To account for the peroxide effect, it has been proposed that anti-Markovnikov addition in the presence of peroxide takes place through free radicals and not through ionic particles as explained below. The initial step in the free radical mechanism is the decomposition of peroxide to yield free radicals. The free radical thus formed abstract hydrogens from hydrogen bromide to form bromine free radicals. Step 2, bromine radicals in turn add on to the double bonds and thus convert the alkenes into another free radical. Step 3, this free radical abstract a hydrogen from another molecules of hydrogen bromide to form the final product as well as a new bromine radical. Step 4, the bromine radicals continues the chain by repeating the step 3 and 4 as depicted. The step 1 and 2 are chain initial step, while the step 3 and 4 are chain while step 3 and 4, which are repeated again and again, constituted chain propagation step. This mechanism is supported by the fact that only a small quantity of peroxide is needed for the process because it is required only for initiating the reaction. Similarly, the fact that addition of a small quantity of an inhibitor such as hydroquinone can prevent the additions according to peroxide effect also supports the mechanism. The inhibitors can obviously break the chain process by forming unreactive particles. Let us now consider the addition of HBr to unsymmetrical alkene in the presence of peroxides according to the above mechanism. In step 3, bromine free radical preferentially adds to carbon 1 of propylene to produce a secondary free radical. If the bromine were to add to carbon 2, the radical formed would be primary free radical, which is less stable than the secondary radical. The reaction of secondary radical with HBr in step 4 naturally give rise to N-propyl bromide. Thus, the anti-Markovnikov addition of HBr can be justified in terms of the ease of formation and stabilities of intermediate free radical formed in chain propagating step 3. Non-application of peroxide effect for the addition of HCl and HA. It may be noted that unlike the addition of HBr, the peroxide effect is not observed in the addition of HCl or HI to unsymmetrical ethylenic bond. In case of HCl, that is probability due to the fact that HCl bond 430 kJ more inverse is stronger than HBr bond 368 kJ more inverse and is not broken symmetrically by the free radical generated by peroxide. As such, free radical addition of HCl to alkenes is not possible. In case of HI bond 297 kJ mole inverse is not double weaker than HBr bond and can be cleaved symmetrically, but the iodide atoms thus formed readily combine themselves to form iodine molecules rather than to add ethylenic bond. Relative reactivities of alkenes in electrophilic addition reactions. The rate controlling step in the electrophilic addition of halogen acids and other reagents to alkene is step 1, which involves the formation of carbocations. It has also been learned that this isoformation and relative stabilities of carbocations follows the order tertiary, then secondary, and then primary. This means that an alkene which gives rise to a tertiary carbocation would undergo addition more readily than another which forms a secondary carbocation. Similarly, the alkene forming a secondary carbocation would be more reactive than one which forms a primary carbocation. In short, the relative reactivities of alkenes depends upon the ease of formation and stabilities of intermediate carbocations. As such, the alkene shows the following order of reactivities towards electrophilic addition reactions. In case of substituted alkenes, the relative reactivities are determined by the nature of the substituent groups. If the substituent groups is an electron attracting group such as halogen, it destabilizes the intermediate carbocation and decreases its ease of formation. In other words, such groups decreases the reactivities. For instance, the reactivity of CH2 double bond CHBr is less than that of ethene because of the presence of electron attracting bromine. On the other hand, presence of electron releasing group stabilizes the developing carbocation and increase its ease of formation. As such, this group contributes towards greater reactivity. Addition of sulfuric acid, cold concentrated sulfuric acids add on to alkene to form alkyl hydrogen sulfates. The mechanism of addition is similar to that in case of hydrogen halides. It may be pointed out that alkyl hydrogen sulfates are easily hydrolyzed to form alcohol alcohols. For example, ethyl hydrogen sulfate plus water on heating gives ethyl alcohol plus sulfuric acid. As such, addition of sulfuric acid to alkene followed by hydrolysis of with water constituent a convenient method for the manufacture of alcohol such as ethyl alcohol, isopropyl alcohol, etc. Addition of water. The more reactive alkenes directly add in water in the presence of dilute acids to yield alcohols. The reactions also take place by electrophilic addition mechanism. Similarly to the addition of protic acids, addition of halogens, alkenes undergoes addition of chlorine and bromine at low temperature in an inert solvents like carbon tetrachloride to form vicinal dihalide. In these reactions of an alkene with bromine, the red color of bromine is discharged due to the formation of dibromide, which is colorless. Therefore, this reaction is used as a test for the presence of carbon-carbon double bond in a molecule. Addition of fluorine to alkenes is not carried out since it causes extensive cleavage of the molecule. In case of addition of iodine, vicinal iodides are formed, are highly unstable, and eliminate iodine immediately to form the double bond. It may be noted that unlike halogen substitution of alkenes, the addition of halogens to alkenes gives only one product in nearly quantitative yield mechanism. It was believed earlier that the addition of halogens to alkenes take place through electrophilic addition process involving carbocation intermediate, as in the reaction with halogen acids and other protic acids discussed so far as given below. The halogen molecule is normally non-polar in nature, but as it comes close to the alkene molecules, the pi electron cloud of the double bond begins to repel the electron cloud of halogen molecules. As a result, the electrons of halogen molecules get displaced towards the halogen atoms away from the alkene molecules. This results in polarization of the halogen molecules, the atom nearer to alkene becoming relatively positive and the other negative. The positive halogen of the polarized molecule is immediately abstracted by the alkene to form an intermediate carbocation and a negative halide ions. This constitutes the rate controlling step of the reaction. In the second step, the carbocation and negative halide combine to yield the dibromide. The two-step ionic mechanism is supported by the fact that in the presence of anions of another halogens, the addition reaction with the given halogens give a product containing different halogens atoms in addition to the normal product. For example, in the presence of chloride ion from aqueous NaCl's, addition to bromine to ethylene gives a mixture of CH2Br, CH2Cl. This is because carbocation formed in the first step can react either with the bromide ion, also from first step, or chloride ions from aqueous NaCl to form two different products. Limitations of above mechanism. The mechanism described above fails to explain two important observations. First, the stereochemistry of addition of halogens. The addition of halogens to an alkene proceeds almost completely in trans manner. According to the above mechanism, the addition of secondary halogens to the carbocation formed in the first step could take place either from the same side or from the opposite side. Non-formation of rearranged product. Reactions involving carbocation intermediate as postulated in above mechanism should be accompanied by the formation of rearranged product wherever possible, but there is no formation of rearranged product during the addition of halogens to alkenes. Cyclic halogen ion mechanism. To overcome the limitations of the above mechanism, it too has been suggested that the addition of halogens to alkenes involves the formation of a new kind of cyclic ions known as halogen ions rather than a simple carbocation as explained below. As the halogen molecules approaches the alkenes and get polarized, the positively polarized halogen end forms a pi complex with the pi electrons of the alkenes. This complex in turn undergoes heterolytic cleavage of the halogen-halogen bond, giving rise to a cyclic halogen ions and the negative halide ions. The halogen ion has a halogen atoms bonding to two carbon atoms by a sigma bond to each. The pair of electrons of one sigma bond has comes from the pi bond of the alkene, while the pair of electrons of the other sigma bond is provided by bromine atoms out of its lone pair of electron. Finally, the halide ions produced above attacks one of the carbon atom of the halogen ions from the side opposite to that of which positively charged bromine is present, because which involves minimum steric hindrance, giving rise to the formation of the dihalide by trans additions. The mechanism involves the electrophilic additions to alkenes through the intermediate formation of cyclic helium ions was initially proposed to explain the observation that the reactions led to trans addition. This stereospecific nature of the reactions cannot be justified if the addition were to take place through the intermediate formation of carbocations as in the addition of protic acids. In the last few years there has been some evidence to prove that the cyclic helium ions do actually exist. Formation of halohydrins. The reactions between alkenes and chlorine or bromines in the presence of water leads to the formation of halohydrins, that is compound containing halogen and hydroxyl group on adjacent carbon atoms in addition of two dihaloderivatives. For example, ethylene plus bromine plus water gives ethylene bromohydrine. Mechanism. The overall reaction consists in the addition of elements of hypohalous acid, but the actual process proceeds through the attack by polarized followed by water. Addition of alkanes, alkylations. Alkenes can also add on alkanes in the presence of suitable acidic catalysts to form higher alkanes. The reactions known as alkylation is employed commercially for the manufactures of alkanes such as 2,2,4 trimethyl pentane used as aviation fuel. For example, isobutylene plus isobutane in presence of sulfuric acid gives 2,2 trimethyl pentane. Mechanism. Alkylation is believed to take place through electrophilic mechanism involving the intermediation formation of carbocations. Addition of alkenes, polymerization. Under suitable conditions, molecules of an alkenes can undergo together to form large molecules called polymers. The reaction taking place is known as polymerization. Polymerization of alkenes is also known as addition polymerization or vinyl polymerization. A few examples of polymerizations of alkenes are given below. Formation of polyethylene or polyethene. These days, two types of polyethenes are produced which have widely different properties as given below. First, low density polyethene. It is manufactured by heating very pure ethylene at 463-483 Kelvin under a pressure of 1500 atmosphere in the presence of traces of oxygen. Low density polyethylene is chemically inert, tough but flexible and a very poor electrical conductor. Then high density polyethylene. It is generally manufactured by heating ethylene to 333 to 343 Kelvin under a pressure of 6 to 7 atmosphere in the presence of a catalyst such as triethyl aluminum and titanium tetrachloride, also known as Ziegler catalyst. High density polyethylene is also chemically inert but is tougher and harder and has greater tensile strength and no low density polyethylene. Formation of polypropylene or polypropene. It is prepared by passing propylene through an hexane, which is an inert solvent containing triethyl aluminum at 373 Kelvin under 10 atmospheric pressure. Propylene can also be manufactured by other method and it possesses different characteristics depending upon its method of formation. Formation of polystyrene or styrene. It is prepared by polymerization of styrene in the presence of benzoyl peroxide. Polystyrene is a lightweight material having good electrical properties. Hydroboration oxidation of alkenes. When treated with diborane, alkenes undergoes hydroboration to form alkyl boranes. The alkyl boranes are readily oxidized by hydrogen peroxide in alkaline solution to form alcohols. Thus, the net result of these reactions also is the addition of waters to alkenes to form alcohols. For example, ethylene plus the diborane gives ethyl borane, with the ethene gives diethyl borane, with the ethene gives triethyl borane. In the first case of hydrogen boration, addition of BH3 to the carbon-carbon double bond takes place with the hydrogen getting attached to one carbon and bonding to the other to form monoalkyl borane. In the second stage, monoalkyl borane adds to a second molecules of alkene to form dialkyl borane, which in turn adds to third molecule of alkenes to give trialkyl borane. The alkyl boranes are not isolated but are oxidized in the same reactions vessels when the boron parts get replaced by OH group to generate the alcohols. The complete reaction may be represented in general as this. Note: the reagent diboron is generally obtained by reactions between sodium borohydride and boron trifluoride. Diboron is actually a dimer of borane, which is however not known to exist as such, but in reaction in solvent such as ether or tetrahydrofuran, diboron behave as if it is consisted of BH3 molecules. In fact, when dissolved in tetrahydrofuran, diboron dissociated to form two molecules of a complex with the solvent. Therefore, hydroborations can also be conventionally carried out with the solution of diboron in tetrahydrofuran, which is commercially available. Orientations of hydroboration oxidation is also a regioselective reaction, and the alcohol obtained is such as if antimarconic of addition of water to alkenes had take place. As such, this method can be used for the preparation of alcohols which cannot be prepared by other method of hydrations of alkenes. For example, acid catalyzed hydration as well as oxymercuration demercuration of hydration of alkenes. For example, acid catalyzed hydration as well as oxymercuration demercuration of propene yields 2 propanol, while its hydroboration oxidation give rise to 1 propanol. Propene plus H2O H positive gives 2 propanol. Some more example of hydroboration oxidations are as follows: 3,3-dimethyl 1-butene in presence of diborane and H2O2 OH negative gives 3,3-dimethyl 1-butanol. It must be noted that due to antimarconic of orientations, only primary and secondary alcohols can be obtained by this method. Mechanism of hydroboration oxidations. Even though the overall sequence of hydroboration oxidations of alkenes appears to go against the Markovnikov rule, yet fundamentally this reaction also involves electrophilic addition reactions to carbon-carbon double bond as discussed below. Hydroboration: as already stated, diborane behave in its reaction as if were getting dissociated to form BH3. Now in BH3, boron has only 6 electrons in its outermost energy level and is therefore highly electron deficient or acidic in nature. This electrophilic boron of borane seeks out the pi electrons of carbon-carbon double bond and begin to attach itself to the less substituted carbon of the double bond. The attachment of boron to the less substituted carbon of the double bond can be justified in terms of steric as well as electronic factors as well. The less substituted carbon is less crowded and can be more easily attacked by the bulky boron containing group. The attachment of boron to the less substituted carbon makes the more substituted carbon develop a partially positive charge. This carbon is better able to accommodate the positive charge since it carries electron releasing alkyl group. As the electrons shift away from the more substituted carbon of the double bond, the carbon becomes more and more electron deficient. As such, it begins to take away a hydrogen attached to boron along with the pair of electrons of the hydrogen boron bond. In this way, we get a transition stage which may be depicted as shown on the right. In the transition state, C2 still has a partial positively charged while B has partial negatively charged. As the loss of pi electrons by C2C1 B bond is more than its gain of electron by the partial formation of its bond with hydrogen. The transition state ultimately generates the alkyl borane in which boron hydrogen bond has been cleaved and the new carbon 2 hydrogen bond has completely formed. It may be noted that unlike ordinary electrophilic addition reactions, hydroboration does not involve the intermediate formation of carbocation. Oxidations of alkyl boranes. The mechanism of oxidation of alkyl boranes by alkaline hydrogen peroxides involves nucleophilic attack by hydroperoxide ions and may be summed up as follows: oxymercuration demercurations of alkenes. When treated with mercuric acetate in a water tetrahydrofuran solutions, alkenes form hydroxy mercurial compounds. These mercury compounds are reduced by sodium borohydrides to yield alcohols. In the first step, the water and mercuric acid add to the double bond. This is known as oxymercuration. In the second step, Sodium bihydrohydride reduce the mercurial compound and the mercury acetate groups get replaced by hydrogen. This is known as demercurations. Both the step takes place very rapidly and conveniently at room temperatures. The organomercurial compound formed in the first step is not isolated but is reduced in situ by sodium borohydride to form alcohol in high yield, that is more than 90%. Oxymercuration demercuration is highly residue selective and the alcohol formed in is accordance with Markovnikov rule. Thus the overall reactions may be summed up as follow: ethene plus Hg plus tetrahydrofuran water in presence of NaBHO4 gives ethanol. In writing these reactions, acetate group is often abbreviated as OAC. A few specific examples of the reactions are as follows: 1 pentene in presence of mercuric acetate and tetrahydrofuran water gives this compound, and which in presence of NaBH4 gives 2-pentanol. Like direct hydrations of alkenes, alcohol formed in these reactions also correspond to Markovnikov rules. Therefore, primary alcohol except ethanols cannot be prepared by this method. Mechanism: the proposed mechanism for the reactions may be described as follows: oxymercurations. To start with, electrophilic attack by the mercury species mercuric acetate at the less substituted carbon of the double bond, that is the carbon which carries greater number of hydrogen, take place to form a mercury bridged carbocations. The cation is immediately attacked by nucleophilic solvent, that is water, to yield the hydroxy mercurial compound as shown below. Demercurations: the hydroxy mercurial compound undergoes demercurations on reductions with NaBH4 to form alcohols. This mechanism is supported by the following facts: it can justify why orientation of additions correspond to Markovnikov rules, since Hg gets attached to the carbon carrying greater number of hydrogens while OH goes to the carbon having lesser number of hydrogens. It also explains the absence of rearrangement taking place during the reactions, since no open carbocation intermediate is involved in the proposed mechanism which can undergo rearrangement. Addition of carbons: alkenes undergo addition reactions with carbons both in the singlet and triplet forms to form cyclopropane derivatives. The reactions is known as cycloaddition because the ring is generated as a result of the reactions. Since free carbons are too reactive to be isolated, the reactions is usually carried out by using a carbene precursors which generate the carbene under suitable experimental conditions. For example, when treated with diazomethane or ketenes in the presence of light, alkenes add on methylene to form cyclopropane derivatives. Addition of substituted carbons: alkenes can add on substituted carbons such as dichlorocarbons to form cyclopropane system. For example, when 2-butene is treated with chloroform in the presence of potassium tertiary butoxide, 3,3-dichloro-1,2 dimethyl cyclopropane is formed. The reactions involves the addition of dichlorocarbons in the singlet form. It is stereospecific and take place by electrophilic mechanism. Addition of free radicals: it has already discussed that the anti-Markovnikov addition of hydrogens bromide to alkene in the presence of peroxide take place through a free radical mechanism. Since the discovery of peroxide effect in 1933, the addition of some other reagents to alkenes in the presence of peroxide or light has also been found to involve a similar free radical mechanism. For example, the addition of carbon tetrachloride to an alkene in the presence of peroxide. Oxidation reactions: alkenes form a variety of products on direct oxidations with different reagents under different conditions. While some of the oxidation reactions merely involves additions to the ethylenic bond, others brings about a complete cleavage of the double bond. We will first discuss only the former type of reactions, while the later type of reactions are discussed under cleavage reactions. Oxidation with aqueous potassium permanganate solutions: when alkenes are treated with dilute aqueous solution of potassium permanganate, a hydroxy group is added to each of the doubly bound carbon atom, resulting in the formation of vicinal glycols. The reactions take place in a cis manner and is commonly termed as hydroxylation. Alkene plus water plus oxygen in presence of cheminoform gives glycol. For example, propylene plus H2O plus oxygen in presence of cheminophore gives propylene glycol. As potassium permanganate get decolorized in this reaction, it can be used as a test for the presence of ethylenic bond in a molecules. The test is generally called Bayer's test. Mechanism: the reaction is believed to take place through the formation of an intermediate to cyclic management species which get to hydrolyze to give the glycol. Besides aqueous potassium permagnetic solution, osmium oxide can also be used for bringing about the hydroxylations. These reactions can involve cis hydroxylation and proceeds via cyclic osmate intermediate. The intermediate is hydrolyzed with NaHSO3 solution to get glycol. Oxidations with peroxy acids, epoxidations. Alkenes react with peroxy acids such as peroxyacetic acid or peroxybenzoic acids to form epoxides, also known as oxidants. Epoxides are compounds having three membered rings, one of the atoms of which is oxygen. The reaction involves the formation of epoxides is sometimes referred to as epoxidation. Mechanism: these reactions involve the transfer of an oxygen atom of the peroxy acid to alkenes. The reaction is believed to proceed by the following mechanism. Ethylene can also form an epoxide merely by heating in air in the presence of a silver catalyst. Epoxides also form vicinal glycols on hydrolysis with boiling water, but it gives rise to trans product substitutions reactions. Allylic halogenation: with the exceptions of ethylene, all other alkenes contain one or more alkyl groups attached to one or both the doubly bound carbon atoms under suitable conditions. These alkyl groups undergo can undergo substitution reactions similarly to those of alkenes. For example, when propylene is treated with chlorine at 775 Kelvin, it undergoes substitutions of the alkyl group rather than addition at the double bond. This type of reaction, where substitutions take place at the alpha carbon atom with respect to the double bond, is referred to as allylic substitutions. The hydrogen attached to alpha carbon with respect to double bond are called allylic hydrogens. Mechanism: allylic substitution is believed to take place through free radical mechanism, as in case of alkenes. It appears rather supporting that the halogen atom generated in step 1 does not to add across the double bond, as in case of addition of HBr in the presence of peroxide. It was suggested by Brown that a halogen atom does add to the double bond, but due to at high temperature it gets eliminated before the intermediate free radical A can add another halogen. An excellent reagent for the bromination of alkene at the allylic position is N-bromosuccinamide. Substitutions of vicinal position. An interesting reaction is that they can undergo electrophilic substitutions at the doubly bound carbon atom. For example, when an alkene is treated with an acid chloride in the presence of anhydrous aluminum chloride, it gives rise to an alpha beta unsaturated ketones. The reaction is comparable to Friedel-Crafts acylation of benzene. Mechanism: in the presence of anhydrous AlCl3 acid, chlorides generate acylium ion which attacks the double bond to form a carbocation. The carbocation loses product to yield alpha beta unsaturated ketone. Cleavage reactions: ozonolysis. Alkenes undergo certain reaction in which the double bond is completely broken and the alkene molecules changes into a smaller fragment. Such reactions are termed as cleavage reactions. The most important cleavage reactions of alkenes is ozonolysis, that is the cleavage of the double bond with ozone. The complete reaction consists of addition of ozone to the double bond to form an ozonide, followed by the decomposition of the ozonide to yield the lower fragment, which consists of aldehyde and or ketones. The decomposition is generally carried out in the presence of a reducing reagent such as zinc dust or water. If the ozonides are decomposed only with water, H2O2 produced during the reactions would oxidize the aldehyde initially formed to the corresponding acid. Zinc does not follow further oxidations to take place. Let us now consider the two stages of the reaction separately. Addition of ozone. Ozonizations. Ozone react vigorously with alkene to form a highly unstable compound called initially ozonide or molozonide, which undergoes spontaneously rearrangement to give relatively more stable product called ozonide. Ozonolysis. The ozonides are themselves unstable compounds. They are not isolated but are reduced directly with zinc and water to aldehydes or ketones. Application of ozonolysis. The final product obtained by the ozonolysis of alkenes consists of one or more aldehyde and ketones depending upon the nature of the group attached to doubly bound carbon atoms. It may be noted that if the carbon forming the double bond carries a hydrogen attached to it, it will give rise to an aldehyde. If it carries only alkyl group attached to it, it would form a ketone. For example, 2-methyl-butene gives propanone and ethanol. Since no two different alkanes can give the same combinations of aldehyde or ketone, as the final product is generally employed for locating the positions of double bond and identification of alkyl group present in an alkane. Thus, ozonolysis plays an important role in the structural determination of organic compound, though their degradation into simpler fragments. Illustrations of the application of ozonolysis. Let us try to locate the double bond and identify a 6 carbon alkene which yields a mixture of acetone and propanol aldehyde. In ozonolysis, acetone contains 2 methyl group attached to carbonyl carbons, while propanol aldehyde has one ethyl group and one hydrogen attached to carbonyl carbon. We know that during ozonolysis, it is the doubly bound carbons which change into carbonyl group. Therefore, it can be concluded that one of the doubly bound carbon of the given alkanes carries 2 methyl groups, while the other doubly bound carbons carries one ethyl group and one hydrogen. Therefore, the given alkene should have the structure this. The double bond is obviously located between carbon 2 and carbon 3. The complete sequence of reactions may be depicted below. 2-methyl 2-pentenes gives ozonolysis gives acetone and propanol aldehyde. Simplified procedure for identification. There is a simplified two-step procedure for the location of double bond and identification of alkanes as shown below. Write the structures of the product of ozonolysis with carbonyl group facing each other. Remove oxygen atoms from carbonyl atom and connect them by a double bond. Action of hot concentrated solution of potassium permanganate. Oxidations of alkenes with hot concentrated solution of potassium permanganate, generally in alkaline medium, also brings about the cleavage of the molecules. The product form consists of different combinations of carboxylic acids, ketones and carbon dioxide, for example given below. This method can also be used for the location of double bond in a molecule. Combustion. Alkenes are completely oxidized to carbon dioxide and water when burned in air or oxygen. For example, ethene with 3 mole of oxygen gives 2 mole of carbon dioxide and 2 mole of water. Thank you.